Hello everyone, let's review the ring theory semester of the algebra module. First, let's define a ring. A ring R with addition and multiplication is a set R together with two binary operations, addition from R cross R to R and multiplication from R cross R to R, such that, first, R with addition is an abelian group with identity element 0. Second, multiplication is associative, i.e. in brackets a dot b dot c is equal to a dot b dot c for all a, b, c in R. Third, there exists an identity 1 in R for multiplication, i.e. 1 dot a is equal to a, which is equal to a dot 1 for all a in R and 1 not equal to 0. Fourthly, multiplication is distributive over addition, i.e. a dot b plus c is equal to a dot b plus a dot c, and a plus b dot c is equal to a dot c plus b dot c for all a, b, c in R. Now, let's discuss some results for a ring. For a ring R, its additive identity 0 and its multiplicative identity 1 are unique, and the additive inverse minus a of any element a in R is also unique. Moreover, for all a, b and R, we have that 0 times a is equal to 0, which is equal to a times 0, a times minus b is equal to minus ab, which is equal to minus a times b, and minus a times minus b is equal to ab. Now, let's define a type of ring called a commutative ring. A ring R with addition and multiplication is commutative if the multiplication is commutative, i.e. if a dot b is equal to b dot a for all ab in R. Then, let's define a subtype of a commutative ring, a field. A field is a commutative ring R such that all elements in R without 0 have multiplicative inverses, i.e. for all a in R without 0 there exists b in R without 0 such that ab is equal to 1, which is equal to ba. If f is a field, then we sometimes write f product to mean f without 0. Next, let's discuss subring. Let R be a ring. A subset S of R is a subring of R if it contains the multiplicative identity 1 and it itself is a ring under the same addition and multiplication as R. Hence, a subset S of R is a subring of R with addition and multiplication if and only if 0 and 1 are in S, S with addition is a subgroup of R with addition, and S is closed under multiplication, i.e. for all AB in S, AB is in S. Next, let's define the product ring. If R and S are rings, then the product R times S has elements of the set containing Rs for all R in R and S in S, with addition defined as Rs plus R dash S dash is equal to R plus R dash with S plus S dash, and multiplication Rs times R dash S dash is equal to R dash S S dash. Next, let's discuss the matrix ring over a ring. Given any ring R, we can form the matrix ring over R, denoted M of n and R, for any n greater than or equal to 1. It is commutative if n is equal to 1 and R is commutative, and otherwise is non-commutative. We want to move on to integral domains, so we need to define zero divisor. If AB in R without 0, such that AB is equal to 0, then A and B are zero divisors, also known as divisors of 0. Then, let's define an integral domain. An integral domain, also known as an ID, is a commutative ring which has no zero divisor. Hence, a commutative ring R is an integral domain if and only if, for all A, B and R, A times B equaling 0 implies that A equals 0 or B equals 0. Next, let's discuss some results for integral domain. First, any field is an integral domain. Also, any subring of an integral domain is also an integral domain. Hence, every subring of a field is an integral domain. We also have a cancellation result, which says that if R is an integral domain, and if A, B, C in R, with A not equal to 0, then A, B equaling AC implies B equals C. We also have that every finite integral domain is a field. Next, let's discuss how modular arithmetic and integral domains relate. If n is in the natural numbers with n greater than or equal to 2, then z mod nz is an integral domain, and hence a field if and only if n is a prime number. Now, we want to move on to polynomials, so let's first discuss monomial. A monomial in x with coefficient in r is an expression of the form a times x to the n, some n a natural number, with a in r without 0. We say that a monomial a x to the n has degree n, and that the coefficient of x to the n is a. The monomials of degree n, together with 0, form an abelian group under the addition expression a x to the n plus b x to the n is equal to a plus b times x to the n. If a x to the m and b x to the n are two monomials of degree m and n respectively, then we define their multiplication as a x to the m times b x to the n is equal to ab x to the m plus n. Hence, let's define a polynomial. A polynomial in x with coefficient in r is a finite sum of monomials in x with coefficients in r. We denote the set of all of these polynomials as r adjoin x. The degree of a non-zero polynomial p of x in r adjoin x is defined to be the largest degree of a monomial which is a summand of p of x. If the degree of p of x is 0, or if p of x is equal to 0, then we say that p of x is a constant polynomial. Note that our definition of polynomials includes the zero polynomial, as 0 is the sum of no polynomials. However, the degree of the zero polynomial is undefined. Next, let's define addition and multiplication for polynomials. Suppose p of x is equal to the sum from I equals 0 to infinity of a sub I x to the I, and q of x is equal to the sum from j equals 0 to infinity of b sub j x to the j, and they're both polynomials in r adjoin x. Then p of x plus q of x is equal to the sum from k equals 0 to infinity of c sub k x to the k, which is in r adjoin x, where c sub k is equal to a sub k plus b sub k. And p of x times q of x is equal to the sum from k equals 0 to infinity of d sub k x to the k, which is in r adjoin x, where d sub k is equal to the sum from r equals 0 to k of a sub r times b sub k minus r. Note that it's dangerous to think of polynomials as functions. For example, x and x squared are different polynomials in f sub 2 adjoin x, but they define the same function from f sub 2 to f sub 2. Now, let's discuss results of polynomial rings over commutative rings. Let R be a commutative ring, then R adjoin x is also a commutative ring. Also, the set of constant polynomials a times x to the naught, where a is in R, is a subring of R adjoin x, which is isomorphic to R. If R is an integral domain, then for any f and g in R adjoin x without 0, we have that the degree of f of g is equal to the degree of f plus the degree of g. If R is an integral domain, then R adjoin x is also an integral domain. Now, let's move on to defining a ring homomorphism. Let R and S be two rings. A function phi from R to S is a ring homomorphism if for all a and b in R, we have that first, phi of the identity element in R is equal to the identity element in S, i.e. phi maps the multiplicative identity of R to the multiplicative identity of S. Second, phi of a plus b is equal to phi of a plus phi of b, i.e. phi is a group homomorphism from R with addition to S with addition. Third, phi of AB is equal to phi of A times phi of B, i.e. phi preserves multiplication. Therefore, let's define a ring isomorphism. A ring homomorphism, which is bijective, is a ring isomorphism. If there exists a ring isomorphism between R and S, we say that R and S are isomorphic, and we denote this by this notation here. Another way of defining a ring isomorphism is that a ring homomorphism phi from R to S is an isomorphism if and only if there exists another ring homomorphism psi from S to R, such that psi circ phi from R to R is the identity function on R, and phi circ psi from S to S the identity function on F. Now, let's move on to defining ideals. Let R be a ring. A subset I of R is an ideal of R if first, I with addition is a subgroup of R with addition. Second, all R in R and A and I, we have that AR is in I and RA is in I. Alternatively, we can say I is an ideal of R if and only if 0 is in I, and for all AB in I, we have A plus B is in I, and for all R in R, A and I, we have the AR is in I and RA is also. Hence, let's discuss some results for ideals. Let R be a ring, and let I and J be two ideals of R. Then I intersect J and I plus J, defined to be the set of all I plus J where I is in I and J is in J, are both ideals of R. Next, let's define the ideal generated by an element. If R is a commutative ring and C is in R, then CR, which is the set of all CR where R is in R, is the ideal generated by C. We denote it as C in bracket. If R is non-commutative, then we say that C in bracket brackets is equal to RCR, which is a set of all RCS where R and S are in R, and we denote this as the ideal generated by C. Next, let's define the ideal generated by a collection of elements. Let R be a commutative ring, and let C1 to CT be in R. Then the ideal generated by C1 to CT is equal to C1 R1 plus all the way up to CT RT, where R1 to RT are in R, which is equal to C1R plus all the way up to CTR, and that is defined as the ideal generated by C1 to CT. Now we want to move on to quotient rings, so let's first make some remarks. Let R be a ring, and let I be an ideal in R with I not equal to R. Then R over I, which is the set of all R plus I where R is in R, is a quotient group. Also, A plus I is equal to B plus I if and only if A minus B is in I. Therefore, let's define the quotient ring. Let R be a ring, and let I be an ideal in R with I not equal to R. Then R over I with addition and multiplication is the quotient ring where addition on R over I is given by A plus I plus B plus I is equal to A plus B plus I. The additive identity is 0 plus I, where 0 is the identity element of R with addition. Multiplication on R over I is given by A plus I times B plus I is equal to AB plus I. The multiplicative identity is 1 plus I, where 1 is the identity of R with respect to multiplication. Next, let's define the quotient map. If I not equal to R is an ideal in a ring R, then the quotient map is a surjective ring homomorphism pi from R to R over I, defined by pi of R is equal to R plus I for all R in R. Then let's define a maximal ideal. Let R be a ring, and let I be an ideal of R. We call I a maximal ideal if I does not equal R, and whenever J is another ideal that strictly contains I, then J is equal to R, i.e. I being a subset of J implies that J is R. Now let's discuss how maximal ideals relate to field. Let R be a commutative ring, and let I be a subset of R which is an ideal. Then R over I is a field if and only if I is a maximal ideal. Next, let's define the kernel and the image. Let R and S be two rings, and let phi from R to S be a ring homomorphism. Then the kernel of phi is ker phi, which is equal to the set of all R in R such that phi of R is equal to 0, and the image of phi is im phi, which is the set of all phi R where R is in R. Now let's discuss some results for the kernel and the image. Let R and S be two rings, and let phi from R to S be a ring homomorphism. Then ker phi is an ideal of R, and im phi is a subring of S. We have that phi is injective if and only if the kernel of phi is equal to 0, and phi is surjective if and only if the image of phi is equal to S. Next, let's move on to state the first isomorphism theorem for rings. Let R and S be two rings, and let phi from R to S be a ring homomorphism. Then R over the kernel of phi is isomorphic to the image of phi. Next, let's state some results of the first isomorphism theorem for rings. We have that S is isomorphic to a subring of R if and only if there exists an injective ring homomorphism S to R, and S is isomorphic to a quotient ring of R if and only if there exists a surjective ring homomorphism from R to S. Next, let's move on to defining units and associates. Let R be a ring. We say that U in R is a unit if there exists V in R such that UV is equal to 1, which is equal to VU, i.e. U has a multiplicative inverse. If U is a unit, we usually write V is equal to U to the minus 1. If R is commutative, we say that AB and R are associates if there exists a unit U in R such that A is equal to UB. Now let's give a quick remark for associate. Let R be a ring, and define the relation tilde on R as for AB in R, A tilde B if and only if A and B are associate. Then tilde is an equivalence relation. Next, let's define a divisor. Let R be a commutative ring, let A be in R with B not equal to 0. We say that A divides B in R if there exists C in R such that B is equal to AC. In this case, we say that A is a divisor of B. Next, let's define an irreducible. A non-zero, non-unit A in R is called irreducible in R if, for all BC in R, we have that A equaling BC implies at least one of B and C is a unit. Hence, the units of R are precisely the divisors of the identity 1 in R. Therefore, we have that if R is an integral domain and A is in R is a non-zero non-unit, then A is irreducible if and only if its divisors are units of R and associates of A in R. Next, let's discuss how commutative rings relate to divisors and unit. Let R be a commutative ring and let C and D be in R. Then CR is a subset of DR if and only if D divides C. And if R is an integral domain, then CR equals DR if and only if C and D are associates. Also, CR equals R if and only if C is a unit. Now, let's move on to defining the division algorithm for polynomials. Let f be a field and let f of x and g of x be in f adjoint x with g of x not equal to 0. Then, there exists q of x and r of x in f adjoint x such that f of x is equal to g of x q of x plus r of x, and either r of x is equal to 0 or the degree of r of x is less than the degree of g of x. We call r of x the remainder on dividing f of x by g of x. Next, let's discuss how units of a ring relate to the units of the polynomial ring. If R is an integral domain, then the units of R adjoint x are exactly the units of R. Now, let's discuss how polynomials and irreducibles relate. If f is a field, a non-constant polynomial f in f adjoint x is irreducible if and only if f cannot be factored as f equals g times h, where the degree of g is greater than or equal to 1 and the degree of h is greater than or equal to 1. We call f reducible if it can be factored as f equals gh, where the degree of g is greater than or equal to 1 and the degree of h is greater than or equal to 1. Next, let's define a root. Let R be a ring and f of x be in R adjoint x. An element a in R is a root of f of x in R if f of a is equal to 0, i.e. when you substitute a for x in f of x, you obtain 0. Now, let's discuss how polynomials relate to roots. Let f be a field and let f of x be in f adjoint x. If alpha in f is a root of f of x, then x minus alpha is in f adjoint x and it divides f of x. Next, let's discuss how roots relate to the degree of a polynomial. Let f be a field and f of x be in f adjoint x. If the degree of f of x is equal to 1, then f of x is irreducible. If the degree of f of x is between 2 and 3, then f of x is irreducible in f adjoint x if and only if f of x has no roots in f. Now, let's move on to defining unique factorization domains. An integral domain D is a unique factorization domain, or UFD, if first, every element of D that is neither 0 nor a unit can be factored into a product of a finite number of irreducible elements. Second, if A is in D without 0 and is a unit, and P1 times all the way up to PR is equal to A, which is equal to Q1 all the way up to QS, are two factorizations into irreducibles, then R equals S and the QJ can be renumbered so that QI and PJ are associates. Next, let's define being prime. Let R be a commutative ring. An element A in R without 0 is prime if A is not a unit, and for all BC in R, if A divides BC, then either A divides B or A divides C. Now, let's give a result for primes. Let R be a commutative ring and let A be an R which is prime. If A divides a product B1 to BR, then A divides BI for some I in 1 to R. Now, let's describe how primes and irreducibles relate. Let R be an integral domain and let A in R be a non-zero, non-unit element. If A is prime in R, then it is irreducible in R. If R is a UFD, then A is irreducible if and only if A is prime in R. Now, let's move on to defining a principal ideal. Let I be an ideal in R. We say that I is a principal ideal if I is equal to the ideal generated by C for some C in R. Next, let's define a principal ideal domain. A principal ideal domain, also known as a PID, is an integral domain for which every ideal is principal. Note that if R is a PID, then R is a UFD. Now, let's define the greatest common divisor. Suppose R is a commutative ring and A and B are in R without 0. We say that D in R is a greatest common divisor, or GCD, of A and B if first, D divides both A and B, and second, if R divides both A and B, then R divides D. Note that in an arbitrary ring, greatest common divisors may not exist, and if they do exist, they may not be unique. Next, let's describe how GCDs and associates relate. Let R be a commutative ring, let A and B be in R without 0. If D is a GCD of A and B, then every associate of D is also a GCD of A and B. If R is an integral domain, then all GCDs of A and B are associates. Then, let's define the lowest common multiple. Suppose R is a commutative ring and A and B are in R without 0. We say that L in R is a least common multiple, or LCM, of A and B if first, A and B both divide L, and second, for all R and R, A and B both divide R, then L divides R. Next, let's discuss some results for LCM. Just as for GCDs, in general, LCMs are not unique. However, as for GCDs, if R is an integral domain, and if L1 and L2 are both LCMs of AB in R without 0, then L1 and L2 must divide each other and hence are associates. Now, let's describe how PIDs relate to GCDs and LCMs. Let R be a PID and let A and B be in R without 0. Then AR plus BR is equal to DR, where D is a GCD of A and B, and AR intersect BR is equal to MR, where M is an LCM of A and B. Now, let's move on to defining a Euclidean domain. Let R be an integral domain. A Euclidean valuation on R is a function delta from R without 0 to the natural numbers, such that for all non-zero AB in R, first, delta of A is less than or equal to delta of AB, and second, there exists Q and R in R such that B is equal to QA plus R, and either R is equal to 0 or delta R is less than delta A. A Euclidean domain is an integral domain on which there exists as a Euclidean valuation. Note that every Euclidean domain is a principal ideal domain, and Euclidean domains are also unique factorization domains. Hence, let's describe how units and Euclidean valuations relate. Let R be a Euclidean domain with Euclidean valuation delta. For A in R without 0, delta of A is greater than or equal to delta of 1, and delta of A is equal to delta of 1 if and only if A is a unit. If BC in R without 0 are both non-unit, then delta of BC is greater than delta B, and delta of BC is also greater than delta C. Also, let's describe how Euclidean domains relate to GCDs. Suppose R is a Euclidean domain with Euclidean valuation delta, and let A and B be in R without 0. Then, there exists E and F in R such that D is equal to AE plus BF, which is the GCD of A and B. Next, let's define the Euclidean algorithm. Let R be a Euclidean domain with Euclidean valuation delta. Given AB in R without 0, do the following to compute a GCD of A and B. Write A is equal to Q1B plus R1, B is equal to Q2 R1 plus R2, R is equal to Q3 R2 plus R3, etc., where delta of B is greater than delta of R1, which is greater than delta of R2, etc., until we obtain Rn is equal to 0. Then Rn minus 1 is a GCD of A and B. Now, let's move on to discussing building finite fields by discussing the following results. If R is a PID and F is in R without 0, then the ideal generated by F is a maximal ideal if and only if F is irreducible. Since every Euclidean domain is a principal ideal domain, this also applies to Euclidean domains. Hence, we have the following recipe for constructing fields. First, take some Euclidean domain R. Then pick out some irreducible element C in R and let the ideal generated by C be the principal ideal in R generated by C. Next, the ideal generated by C is maximal, and hence the quotient ring R over the ideal generated by C is a field. Therefore, we get the following result for polynomials. Let P be a prime and let F be an irreducible polynomial of degree k in F sub P adjoint X, and let I be the ideal generated by F. Then the quotient ring F sub P adjoint X over I is a finite field with P to the k element, and the polynomials of degree less than or equal to k minus 1 in F sub P adjoint X together with 0 form a set of coset representative for F sub P adjoint X over I. And as ever, thank you for watching.